Hello, I'm Tyler Werben. Today we'll be doing recommended problem 651. Um, our original problem states that um, we have a space truss and we're asked to find the force in each member and state whether they're in tension or compression. This is the original problem, and we've modified it a little bit. So we've actually added a new force, and we've changed the distances and the units. Um, so we were given our space truss, um, the distances, the forces acting along each point, and we were also given the types of support. It was a little hard to see, but these are actually ball and pin. So what's required? Well, we need to find the forces in each member, um, whether they're in tension or compression. And then we'll also need to know the Cartesian vector form. That's what I'll be using, but you can also use the scalar method. I just think the Cartesian is a little bit more straightforward. We also need to know how to use the joint method or section cuts. For this specific problem, I'll be using the method of joints. So our assumptions, we're assuming it's in static equilibrium, and this gives us our 6 equilibrium equations. And it's a good point to note that if the system is in equilibrium, so are the joints. The types of pins was a ball and socket, which doesn't allow for any translation in the X, Y, or Z. It does allow for a moment, so there are no moments. And then we'll be using the Cartesian vector form, finding the position vector, then the unit vector, and then we'll use those to determine the force in the member, which leads us into strategy. So we'll actually find each point, and we'll use this to find the position vector, and then the unit vector. We'll use the method of joints to solve the members, and we'll be using this tension technique, which assumes the members are always in tension. And this makes it easier on us. If the value is positive, it confirms its in tension, and if it's negative, it indicates that it's in compression. And then we'll use the equilibrium equations to solve for the forces. So our solution, where do we begin? Well, this isn't a complete free body diagram. We actually need the support reactions. So we have the ball and socket preventing translation in the X, Y, and Z. We have that on D and C. We only have one support reaction on E, and it gave us a little hint in the problem that there's a collinear support member acting along EB. And that's because this member here, it acts like a free hanging member. So it only allows for one support reaction here. But that's 7. That's still 7, which is greater than the number of equations we have to use. So there's no real way we can solve for the support members with the things that we know now without using any tricks. But is it even necessary to find the support reactions? In this case, it's not. We can start at the joint and still find the forces in each member. We will extract some useful information, like the points at A, B, C, D, and E, and then in terms of its position from the origin. So we'll do just that. So A, it's acting 0 in the X, it's acting positive 10 feet in the Y, and then 0 in the Z. And then B, it's again 0 in the X, positive 4 in the Y, and positive 12 in the Z. And then we do that again for C, D, and E. And then this is where we begin our analysis. So we'll focus on point A, we'll zoom in, and we see that we have member AB, AC, and AD. And then, of course, our given force. So here are our points. So we just solve for the position vector. And we got this equation from our formula sheet. And I'll be moving kind of slowly for this first member and then speed up for the next ones because the method is the same for all of them. So please feel free to pause the video, make sure you're tracking and following along. But here we see that it's member AB, and that's because we're assuming the member is in tension, so it's going in that direction from A to B. And in that case, it's the final point minus the initial point. So it's B minus A in the X, Y, and Z directions. So we just plug in our points. And we find our position vector is -6 feet in the Y direction and positive 12 feet in the Z direction. And then we find our magnitude. Again, we got it from our formula sheet. And our magnitude is just the square root of the square of each of the coordinate directions. And it's about the square root of 180, which is approximately 13.4 feet. And we'll use these two to find the unit vector. And the unit vector is stated here under the position vector, and it's the vector divided by its magnitude. And we just plug in the numbers again, and we find that the unit vector, it's unitless, is negative 0.448 in the Y and 0.896 in the Z. We use the unit vector, and again, we use another equation from our formula sheet, and we're multiplying it by the magnitude of the force in member AB. And this is going to give us our vector. So this is the direction, and this is the magnitude. So we don't know the magnitude yet. That's what we're trying to solve for. So we just leave it in its variable form, and we distribute it across our I, J, and K positions. So that's what we're going to save. We're going to save that, put it up here. And then we're going to do the same for member AC. Again, find the position vector, its magnitude, use those two to solve for the unit vector, and then keeping FAC in its variable form, we then distribute it across, and then we'll save this one too, and then again for AD. So same method, same process. And then we were given P, which is acting purely in the negative Z direction. So we'll just rearrange all of our equations. We use our equilibrium equations. And then I'm actually going to color code it so we can clearly see which is what. And then from here, we use our equilibrium equations, and we focus on the same letters. So all of the I's are grouped together, all of the J's and all of the K's are. And then we'll plug in the I for X, the J for the Y, and K for the Z. And then we'll use a little bit of strategy here. We're actually going to start with FZ because we have one unknown isolated, and we can solve for that variable, whereas the other ones have more than one variable unknown. So we'll start with Z, and we just plug in our numbers, and then we solve for FAB. So it's 0.7 divided by 0.896, and then we get approximately 0.781 kips. And it's positive, so we know it's in tension, and that's because we're using the tension technique. So we can cross out our summation in the Z direction, and then it doesn't really matter which one we do. Where I'm going to do X to show the relationship between FAC, and that'll help when we do the summation in the Y direction. So the X direction, FAC is equal to FAD. And that makes sense because they are symmetrically related to one another. So they're equal, just acting in positive and negative X directions. And then finally, we use our some of the forces in the y direction to solve for FAC or FAD because we know FAB. So here we can plug in FAC for FAD, and then rearranging our equation, we have -2 FAC is equal to positive FAB. And then we just plug in our value and we solve for FAC here. And then we find that FAC is negative 0.228 kips. And the negative indicates it's in compression. And then we know that FAC is equal to FAB from this equation above. So that's half of our work done. We found 3 forces in the members. So we're going to save those, put them down here. Now we're going to focus on the point B. So we'll zoom in here. And we couldn't have started at point B because there's 4 unknowns, but now we can move to B because we know the force acting along member FAB here. So we use our points, same method. It's going to get a little crazy on this page, but again, you can pause the video and make sure you're following along, but it's the same method. We find the position vector, its magnitude, we solve for the unit vector, and then keeping FBE in its variable form, we distribute it across the I, the J, and the K directions. And we do that for member BE, member BE, BC, and BD. And then again, we were given our orange tension acting purely in the y direction, positive y direction. And then we solve for our FAB. And so here is our equation from the last slide, and we just plug in what we solved for. Using our 5 equations here, we move forward, and then we're going to try to solve for our unknown variables. And again, I'm going to color code it so we can clearly see which forces are acting along each member. So same process. We isolate the I's, the J's, and the K's, and using our equilibrium equations. And there's no real strategy we can use. There's no isolated variable, so it doesn't matter where we're going to start. In this example, I'm going to start in the x direction just to show the relationship between BC and BD. So we plug in our equations, all the numbers in the I direction, and we find that FBC is equal to FBD. Then we're going to do Z, and this is just to solve for FBC, which in turn solves for FBD. So rearranging our equation, we find that FBC is equal to 0.374 kips. It's positive, so it's in tension. And then finally, we use our some of the forces in the y direction, solving for FBE. We substitute the FBD for FBC, and that's where we get the 2 here. We multiply these across. We add our force, which is 1.4 kips minus 0.35 kips. So the orange force minus the FAB in the y direction force. And we find that our FBE force is 0.817 kips. It's positive, so it's in tension. And then we save these equations. So we found all 6 of the forces along each member, and we've stated that they're in tension or compression. So here's our free body diagram. We didn't really need the support forces, even though it gave us a hint. It wasn't necessary to solve for those. It is important to note that the support at E is acting only in the y direction, but it wasn't necessary. It's necessary for a complete free body diagram, but not to solve for the members along each force. So here are our final answers from the slides above. And we'll rearrange those into pounds. They don't need to be in kips. So in conclusion, is this a reasonable answer? I believe it is reasonable. If we look at our final forces and our diagram here, we see that forces are acting along this point. It's being distributed across BD and BC. We can, guess that those are in tension, equally distributed. FBE is less than the orange force. That makes sense. And AD and AC are in compression with a pink force acting downwards. Now we might think that this force, this member, the blue member, is in compression, and that would only be true if the orange force was the only one acting, but we have this P force, so it keeps it in tension. So going over how we solved for each member, we used the method of joints. We determined the position vectors, then the unit vectors, solving for the forces using the equilibrium equations. There are many ways to solve for the members. For example, we could have used the scalar notation and had multiple 2D free body diagrams. In this example, I found it easier to use Cartesian, good practice, a little bit more straightforward too. And then in the end, we determined whether it was in tension or compression using the tension technique, which is assuming the members are always in tension. If it's positive, it confirms it's in tension. If it's negative, it indicates it's in compression. And that's the end of the video. If you have any comments or suggestions on how I can make this presentation better next time, please let me know. With that said, I hope this helps, and thank you for watching.